Hello, we are Elena Ponce
and Krishna Murali,
and we will be presenting our work, Flight Validation of a Global Singularity-Free Aerodynamic Model for Flight Control of a Tail-Sitter. In it, we investigate challenges in modeling and actively stabilizing a particular class of hybrid air vehicles, namely dual-engine, tail-sitting, flying-wing aircraft, through an ICRA Super-Aero-made design called Mavion. Actuator-wise, the Mavion has two motors and two elevons for airframe control and performing transitions from cruise forward flight to tail-sitting hover flight. The flight transition involves significant changes in the Mavion's angle of attack alpha. The Mavion also encounters unusual 180-degree relative airflow velocity during hover, which is not commonly modeled in traditional flight mechanics. Furthermore, in hovering mode, the direction of airflow, that is, the inexistent airflow in wing sections out of the propeller slipstream, is ill-defined. This situation produces singularities in traditional Buckingham Pi-based flight mechanics aerodynamics modeling. To solve these issues, we have previously developed an aerodynamics framework called Phi theory at our lab. Additionally, Phi theory is optimization friendly since it naturally imposes a global polynomial form on the differential equations of motion. Previous work validated the longitudinal trim points predicted by Phi theory in a wind tunnel campaign. The present work further validates Phi theory, predicting trim points in turn maneuvers and anticipating unstable conditions during flight.
The set of lateral trim points is numerically computed and illustrated in the energy maneuverability or doghouse plot. The resulting points illustrate the reachable flight envelope, which is limited by banking aerodynamics. Aeroelastic and structural considerations could reduce it further, but it is interesting to know the aerodynamic effects already yield envelope restrictions. The fact that control set points are uniquely defined by airspeed and turn rate suggests an intuitive pilot interface, which abstracts the internal workings of the drone. To hold the Mavion at these trim points, a scheduled LQR controller was designed. The number and location in the flight envelope of the scheduled points are decided via a region of attraction analysis. For curiosity, if we use a single instead of scheduled LQR controller tuned for hover flight, instabilities were observed in simulation for velocities greater than 10 meters per second. Simulations showed that using gain scheduled LQR eliminated this instability. These results were verified during flight tests and further validated Phi theory. The predicted instabilities with a single LQR were observed. Finally, as predicted, the scheduled LQR is able to dampen the oscillation previously observed. Thank you.